Thank you for having me. And my great pleasure to give you this overview of our developments. And this talk is, you can see, is endorsed, sponsored, and excited about. I'm excited about Sensor Council and our electronic nose community. Okay, so this talk is about technical developments that we are heavily involved. So you can see that sensitivity, selectivity, and stability, these three words, I'm aware they are in our minds from about 1985, okay? And when I was in grad school, those were my equipment things. As you can see, big impedance analyzers, monochrometers, processors for data analytics offline. So these days we have huge hardware advancements, and I will show you what we can do with these hardware advancements. Edge processors help us to do chemometrics on the edge. There are many synonyms for that. So in my several minutes, I will show what we can do in terms of improvements, what is our vision, and quickly I will show you three examples and what in our opinion, the societal impact is. This slide is nothing new to the team here. And before the sensors, there were regulations to do everything possible to save lives of workers. You can see little by little early sensor developments were happening. These days, they're promising, or the most famous sensors I'm highlighting here. Over time, they became smaller and smaller, we know that. And take-home message from this slide is that they were developed to detect high concentrations, relatively high levels of gases in order to save lives, okay? And over time, they became smaller, we see that, but the principle did not get changed. So you detect high concentration of gas, and we know, of course, that in the ambient conditions, there are many other gases, we can call them interferences, okay? And if I'm detecting high concentration, I don't care. And I will show you more nature quotes, but this one says, yeah, those single output sensors are very good when the pollution levels are very high. So we are happy that there are many different companies that provide these different types of sensing elements. We are the industrial researchers. We are developing sensing elements as well. You can see that in every data sheet, there is a table, and the table says, I have cross sensitivity for different gases. I'm highlighting them here. So nothing new. And what is important is to keep in mind that this cross sensitivity comes from the methodology or detection principle. Okay. So now, if we try to detect relatively small concentrations of gases, I'm highlighting this as analyte gas, the level of interferences does not change. You can see that these are the same levels. Now, in the presence of those interferences, small detection of small gas concentrations becomes a challenge. And you can see the correlation plots here between traditional approved instrument and sensors that anybody can buy on the internet. You can see that the R-squared numbers are not good enough, okay? So on this slide, I'm showing that quote on the left again. And on the right, I'm showing that, yeah, there are other nature quotes. They're saying, don't do this. And EPA and other teams, they're saying, well, new technology developments need to happen. Focus on your hardware community. Please focus on that. So we're the part of analytical instrumentation community. My degree in this country was on analytical instrumentation. And here I'm highlighting that there are orders or different orders of measurements, as Carl Busch and Bruce Kowalski showed some years ago. So the zero order, first order, and second order, zero order are those single output sensors, and no matter what happens, that sensor will have a response, and mathematically there is no way to differentiate between the response to a gas, to interferent, or to maybe drift. You can see the first and second order devices, and these are examples that people are happy to use. And this society recognized these developments and this mathematics, but not with one, but with 3 Nobel Prizes. So my small font here shows, yeah, these are the variables for the first order, second order, and higher order machines. So as a part of that community, we see what we can do better for the next generation sensors. And we're saying, yeah, we need to highlight or focus on how we can excite those individual sensing elements in a different way that is currently done. What can be that physical transducer that can do that excitation? What can be that material that can help us? And what can be that data analysis on the edge or elsewhere to make it happen? So you see examples of different transducers. These are the bullets of wearables that people practice. We're also practicing sensing materials. You will see that more and more interest is in what types of energies to apply to change the parameters of this sensor system. And you see the contemporary electronic components that are integrated circuits and edge processors. So on this busy slide, I will spend 10 seconds on it. What you can see, yeah, classic thermal activation. Wolfgang Gopel and others were showing that from last century. The punchline here is that x-axis is independent variables such as temperature. Good. And we see, yes, depending on the temperature, you see the different profiles for detection of hydrogen or different types of gases. Okay. The middle portion of this slide is photoactivation. So these are more recent papers, and what I'm trying to show here is that independent variable here is light intensity, and people are trying to develop the same philosophies of how to apply that energy to differentiate between different types of volatiles. It's way more recent work. Super recent work is ultrasound activation. I'm happy that our sensing community is picking up of huge knowledge base from catalytic people who have been doing ultrasound a lot. So these are very recent ways of applying another energy. So the 3S enhancements based on these energies are amazing, in my opinion. On the left, I'm showing that, hey, if you do temperature modulation, sometimes you can get the sensitivity enhancement 3,000 times. Okay. For selectivity enhancement, of course, Steve Szymanczyk and others, they were showing temperature modulation with individual sensing elements. These are the way to differentiate between different volatiles. Temperature and UV, very recent work. Many more and more papers are showing that you can differentiate different volatiles. And stability improvement, Andrea Schulze and others, they were showing that, yes, if you do it the right way, you can have way more stable response. So in our research center here in Iskayuna, so we are taking the classic metal oxide sensing materials. Okay, why? Just to show that we can do magic with them. And we show that, yes, if we are measuring conventional resistance, as has been shown initially, then these are the bullets of things that people don't like, especially nonlinear response and so forth. Okay, so if we use the full way of doing the measurements and doing the measurements of impedance with our integrated circuits, then we're getting way more better performance. And here we're showing that we're calling it the electric excitation because we're focusing on the portion of that impedance spectrum, and these are the bullets of why it is useful. These are my 3S improvements where we show the linearity and sensitivity over the broad dynamic range, selectivity with the single sensing element. Selectivity was shown last century as well, and stability of such sensing elements in a nice way. So we are truly standing on the shoulders of giants, as I said, Wolfgang Gopel and Taguchi, and these are the bullets that we showed we commercialized this sensor system, and that's where we are now. A lot of people follow this work, and these are some examples from literature about linearity and stability and recovery speed and so on. So it's nice to see huge body of work in different research groups. We're also applying our modulation tricks, excitation things, in order to make the sensors first order for electrochemical sensors. And here we're showing, with existing components, we can differentiate between different volatiles, either modulation of a bias or impedance measurements, and modulation of other parameters. So these are electrochemical sensors. Our last technical slide to show that we're also operating with optical readouts, so we can call them photonic metamaterial sensors. And initially we showed that with those nanostructures, we had three-dimensional dispersion using PCA squared plot, but in literature, people show that you can get up to 5 PCs if you use single sensing element like that. But very recently, we showed that if we add a second dimensionality, such as angle of excitation, then our number of PCs with a single sensing element is 7. So that's, to us, is quite amazing to see how we can expand these capabilities. And we are the part of electronic neuros community. I'm North American chair, and we are furiously comparing the performance of these individual sensors with the sensor arrays that we have in our labs, and we're quite happy to report our results. So my last slide shows that if we use new philosophy of producing these excitation tricks, like I'm showing here on the left, then we can fit on a coin, but we can have the performance to try to be as good as the conventional analytical devices. And we are really a part of this community, and we are very happy about that. My last slide before the acknowledgements is to show that on the internet, there are commercialized devices that are based on this philosophy. So we showed our sensor system, Bosch and Renesas, they're doing temperature modulation. Nevada Nanotech, they're doing temperature modulation. These guys in Sweden, they're doing the spectral measurements for hydrogen detection. And Andreas has the nice company that is second order devices. So thank you guys for your attention so much, and thank you for this opportunity to present these results. Thank you.
All right, great research
We try.
presentation. I'm not seeing a comment on it. Any questions from our panel that is?
There's a question here from the panel, real quick. We have 1 minute, and then we have a sponsored reading that's coming. So the quick question was, what is the lowest concentration of hydrogen sulfide that you can detect with these sensors?
With hydrogen, not a sulfide, we detect 5 parts per billion. With the H2S, we also, I think, 2 digits ppb levels.
All right.
Why we didn't do thermal modulation, but those people show parts per trillion. So it's something that people can practice for free. Yes. Thank you for this opportunity, guys. Thank you.
All right. Thank you.